Hi, everybody. Today we will see the last part of electromagnetic induction. The first thing that, as a reminder, the first thing I will start with is the magnetic flux, which was B dot A, where B is the magnetic field and A is the area vector. And since this is a dot product or scalar product, it's just BA cosine theta. So suppose this is the area, and area vector is always perpendicular to the area, and the magnitude of the area vector is the area of this circulation. Actually, this circulation is like the wire, and we put this system into the magnetic field, okay, in arbitrary direction. So the magnetic field lines will pass through this loop of coil with one rotation. There may be also more than one rotations. In this case, we will have more EMF, okay, here. So this EMF, or the potential difference at the tips of this coil, is due to the change in the magnetic flux. So we have seen that epsilon is minus n times d phi b over dt. Phi b being BA cosine theta. As you see, in order the magnetic flux change in time, any one of these can change, can give this contribution. So magnetic field can change in time alone, and area of this arbitrary shape can change in time, and also the angle can change. We have seen that. If we let this system to rotate around this axis like that, okay, we can produce an electromotive force, of course, under the magnetic field. Without the magnetic field, none of these things that we are talking about can be said. So the magnetic field should be there, okay? So if you can rotate this thing, it acts like an alternator. Again, epsilon is given by exactly the same expression. So, but this becomes AC, right? So we see that this electromagnetic, this is the electromagnetic induction, okay? This inducted electric field. So the induction electric field will change in time as a sinusoidal wave, okay? Sinusoidal signal. So this is the basics of alternator. So we had seen that, of course, for alternators, we don't have only one winding. We have more than one windings, okay? So since we have this case, we can also connect this equation into the Lenz law. Lenz law stated that if there is a suppose that this is the wire that we are talking about, okay, and these are the magnetic field lines, not necessarily straight. So if B is increasing, now Lenz law actually gives you the information about how B changes in time. So if dB over dt is positive, okay, dB over dt is positive and increasing in time, obviously, so it means that the magnetic field is somewhat increasing in time, like that. In this case, this loop produces its own current, so that induced magnetic field is produced, exactly opposite direction, and similar to this B field. So this is induced magnetic field. Actually, this happens everywhere, not only this one. So the way to create this induced magnetic field is using the right-hand rule, okay, is to pass a current this way. Okay, so the current will be coming to this point and leaving from that point. So this will be plus and minus epsilon if D is increasing in time. This is what we have seen. Okay, so why is it happening? Because we have this expression, as you see, only we have only magnetic field changing, so that epsilon is equal to minus n. Okay, so a and cosine theta are not changing. I'm writing them here. Okay, times dB over dt. This is the magnitude of the electromotive force, or just the potential difference between the 2 points, as you see. Okay, there is a minus sign. This minus sign means that the original original magnetic field is opposed, and induced magnetic field is created. And if dB over dt is positive, then everything is normal, and we have this case. But now what we can do is that we can now reduce the magnetic field. How can we reduce the magnetic field? There are two ways. Maybe one is to have this magnets getting away from the system, or just if it is an electromagnet, the current that produces the magnetic field can be reduced in time. So there are ways to do this, obviously. Okay, we can really do that. But if dB over dt is negative, it means that magnetic field is reducing, but the direction is the same. Then yes, the induced magnetic fields, okay, in this case, the induced magnetic fields will be just opposite to this original case, okay? So the magnetic fields like that, okay? So to accommodate this negative change, the current induced magnetic fields now will be in the same direction with the magnetic field, okay? And the current will be totally in opposite direction, okay? In this case, the current will start from this and go around and come back to this other point. So this will be minus and plus epsilon. As you see, the sign of this potential difference is changed if the magnetic field is reducing in time instead of increasing in time, because there is a minus sign. Two minus signs cancel each other, and then when they cancel each other, as you see, there is no negative sign, so that the induced magnetic field will be in the same direction with the original magnetic field. So the lens law actually states that the coil wants to keep its normal state, which in which no current is passing and no magnetic field is passing through its region. But if there is a magnetic field passing through it, it automatically creates a magnetic field, and it creates an electromotive force between the two tips of this coil itself. But the very important fact is this. Suppose we have a stationary magnet. If B is stationary, it means that not changing. It means that we have this coil sitting there, and we have this magnet, okay? This produces the magnetic field, and the magnetic fields are passing through this coil. Nothing happens. So epsilon is 0. Because in order this to happen, this magnetic flux should change. In other words, either the area should change, or the magnetic field should change, or just the rotation. You should rotate this whole system, as we had done in the alternator case. Without this, if everything is stationary, nothing happens. So also you can do this. You can switch on and off this magnetic field if it is created from a coil, for instance, or just a solenoid, or let's say electromagnet. So you can do these windings, okay, and then connect it to a battery like this, and then put a switch there, okay, put a switch. So if you just turn the switch on and off, okay, like this, push button and then release, push button and then release, right? In this case, you can turn this magnetic field on and off, So this on and off thing will create an electromagnetic force. No problem, because it will change in time. So probably in this case, the magnetic field can be drawn like this: on and off, on and off. As you see, it's like a square wave. You know, this part is on part, this part is off part, and this part is on. So whenever there is a change, so these parts are important. Okay, the change. So as you see here, the magnetic field is reducing. Here, the magnetic field is increasing. So in this case, we have these pulses, right? Positive and negative pulses like that. So during these changes, we have these epsilon, okay? But only during the change. When it is constant, again, nothing happens. So as you see, epsilon is created only at B field changes take place. This is very important, okay? So this is a pulsed electric field we can create by using this electromagnetic, okay, switching back and forth. So we can also do this second example, okay? We can just put a magnet next to it, okay? And we know that the magnetic field lines will be similar to this solenoid case, okay, or electromagnet case. But now we move this back and forth. Move. In this case, the intensity increases and decreases, increases and decreases. If you would do this move continuously, then the magnetic field, okay, will increase, okay, increase and then reduce, increase and reduce. As you see, this is a continuous change. B as a function of time. In this case, epsilon will be positive or negative, depending on if it is increasing. You know, depends on which side you choose to be positive or negative. Doesn't matter. Okay, let's just put these change points here, so that the electric field will be maybe reducing and increasing and reducing, increasing like that, right? The reason that we have a positive changing electric field is because north and south is not flipped over, right? So this is just this kind of move. But now if we flip this magnet over, so there are different varieties of doing this. So it means that we are rotating around this axis. So north is becoming, this side is becoming south and this side is becoming north, like this rotation. So magnet is rotating in this case. So our coil is just sitting there. In this case, we have again magnetic field changing in time, but sometimes it's positive and negative. So depending on north and south, in this case we have also okay epsilon, which is changing also sinusoid. So there are different ways of creating these pulses in these coils. Okay, so now also don't forget this n, which happens to be the number of windings. If you increase the number of windings, okay, like that, and then finally when you're done, you can just get the last part of the tip, and suppose that this is your coil. So what it means that when you increase the number of coils, so the intensity of the signal also gets bigger and bigger and bigger, right? So maybe this is for n equals 3 or something. Okay, so this is really important, because now by changing magnetic field, we're creating an electric field. So as I told you earlier, the electric field is really not taught independently from the magnetic field. Okay, so we had seen this. Also, we would like to. I would like to. I showed you that if we can also write this. Okay, so epsilon is equal to minus n d phi b over the dt is our expression. But we also know that suppose that F equals Q B cross B, right? So now suppose we have this wire, and on the segment of this wire, DL, okay, small segment of the wire, DL. This small segment may be moving with some kind of velocity like this. So it means that I can just hold this part and then just pull a little bit, right? With some kind of velocity. So coil part moving. So the magnetic field is stationary, okay? So the magnetic field is stationary. So B is stationary. In this case, the magnetic field is not changing in time, but some part section of the coil is moving with some kind of velocity. Okay. In this case, the charge, okay, on this part, on this wire will experience this kind of force, right? But now it means that if this is happening, then there is an induced electric field because of the rotation, because of the motional EMF, right? Because of the change in the magnetic flux. Why is the magnetic flux changing? Magnetic field is constant, angle is constant, but the area is changing, as you see. The area is changing because if this section of the wire goes this way, then probably the shape of this wire will be something like that, so that the area will change, okay? The area will change. In this case, only the area is changing. So, but now, so an electric field is created. By the way, we assume that these currents are passing through these wires. It means that the rotating electric field is also created. Okay, rotational electric field is created. So, suppose that this is the current, the electric field will be also along the current. Okay, so we know this is a fact. So, as you see, the electric field will be always perpendicular to the magnetic field. So this is also another thing, important thing. So now, if we want to write this electric field, it's electric field that this little charge experiences. So the electric field will be just equal to F over Q, right? F over Q. So in this case, the electric field in this case for this little charge here will be just V cross B. Okay, V cross B. So, but the potential difference or the voltage is just E times dl. Okay, so this little change in the potential difference is E dot dl. This little segment will create some kind of potential difference between the two ends, and then it will be given by this expression. Okay, so remember that the unit of the electric field was volts per meter. So the electric field is always potential difference divided by some kind of distance, volts per meter. So this is something that we remember from our previous lectures. In this case, since dE is this, we can also write this expression by integrating this to get epsilon, so that this expression can be written as okay, epsilon, which is minus n d phi b over dt, which is also equal to, okay, integral of E dl, integral of E dot dl. Okay, but E can be written as also V cross B dot dl. Okay, as you see now, there is a stationary magnetic field, but the coil is moving. So this is called motional EMF. Also, this can be considered like this. Suppose you're driving a car and there is a magnetic field somewhere, and the velocity of the car actually is the velocity of the coil, and the coil is moving relative to the magnetic field, and then there is a electric field is produced. So this is the same thing that you experience in your radios when you are passing under high voltage lines, okay? Because there are some parasites in the antennas. It's due to the motional EMF. So your circuit in your radio or antenna circuit is moving, and there is a magnetic field. Actually, in the lines case, magnetic field is not constant, but it's changing with 50 hertz, okay? Because the line frequency is 50 hertz, and because of this thing, some kind of little electric field is created, and this causes some kind of parasites. So this is the motional EMF general form. So now also we do this. Okay, this is very important. Suppose that there is a magnetic field inside the page. Okay, so a magnetic field inside the page, like this. Okay, and homogeneous everywhere. Now, if you have a rod like this, okay, metal rod, and if you just move this rod with this kind of velocity to the right, we know that in metal, there is no way that you can create a potential difference unless there is a magnetic field and motional EMF is produced. In this case, the upper part, okay, the upper part and the lower part will have different polarities. So if this is A and B, there will be some kind of VAB, some potential difference is created. And it is called induced electric field, and it's minus, and it's okay, it's just not with minus sign. It's just V cross B dot dl. dl being this distance. In this case, let's say this is dx. Okay, so this dl is a vector, but it may be only one dimensional. In this case, we have to write this as VAB, or induced motional EMF is V cross B, okay, whatever the vector product is, okay, times dx times cosine theta. If this is x direction, and suppose this is x direction, and our rod is moving at a different angle with the velocity. So this is the angle with which this rod moves, and the magnetic field is downward. As you see, it's just a metal moving in the magnetic field. Okay, so automatically some kind of potential difference is created between these two tips. This is called motional EMF. Okay, this is very important. Okay, we had seen this example with the rail. We said that if there is a rail and we can pull this rod to the right like this, okay, since this rod is metal and conductor, it's touching these points, it looks like a coil, and if there is a magnetic field inside or outside the page, doesn't matter the direction, okay. So if this rod moves with some kind of velocity, then there is an area change. In this case, the area is changing. Actually, if V is to the right, it's increasing. So there is dA over dt. dA over dt should be positive because the area is increasing. Okay. So now we know that this area is increasing. So we can now calculate the motional EMF between the two tips, A and B. So VAB or epsilon can be given as just minus BLV. If L is the length of this thing. So how did we find this out? It was very simple. Remember that epsilon was equal to minus d phi b over dt, and it is equal to minus, okay, minus b dA over dt. Why? Because the magnetic flux is just B dot A in our case, okay, but it is BA cosine theta, but theta is 90 degrees. because the area vector is, doesn't matter if it is 180 or 90, 0 degrees. So magnetic field lines are inside the page, and the area vector is either inside the page or outside. They are aligned in the same direction. Okay. So in our case, we can assume that the area vector and the magnetic field vectors are parallel. Okay. This is what we are assuming. So the area vector is downward, and also so is the magnetic field vector. In this case, theta is 0 degrees, not 90. So cosine 0 is 1, so that we have just dA. But now A is the area is the only thing which changes in time, so that D is constant and dA over dt is there. So now, but we know that dA over dt, but dA is nothing but equal to LV times dt. Why? Because this distance, after some time dt, this distance will be given by dx, okay? And dx is just v times dt, because v is constant. Of course, in all these expressions, the velocity is constant. If velocity is changing, then we have some other relationships. But now in this case, it's constant, so that dx can be written as v times dt. But what about the change in the area? This is the change in the area, this part, change in the area. So this dA, which is change in area, how can we calculate this? Of course, now if the rod is here, you get the total area, and then you subtract from this area, the small area, the beginning area that you start out with, okay, before motion. So if you just subtract the big area minus the small area, you get only this little change in the area. This is what, so it's dA is nothing but just L times dx, because this is a rectangular area. So this side is dx and this side is L. Obviously, it's just dA, L times dx. This is how we came up with this expression, because dx is written as v dt like that, and then L is there. So we insert this expression here, so that when we have dA, which is equal to LV dt, dt's will cancel, we get just LV, and this is the expression that we have. Exactly. So epsilon will be just minus dLV. This is the thing that we had derived earlier. But now I will look at this problem from a different perspective, okay? Because now, so the rod will move with a constant speed, right? So as you see, the circuit is completed, and because of this motion EMF, there will be some plus and minus signs, okay? Either upper part will be plus and the lower part will be minus, or just vice versa. Let's check which one is which, okay? Which one is which. Now, if the charge is experiencing a positive charge, is moving in this way, and the magnetic field is downward, let's look at this closely. Don't forget, the whole thing is moving with the velocity v to the right. So the charge now, the charge is also moving. Q is moving with the same velocity, because it is just in this rod. In this case, but we know that the magnetic field is downward. So remember that the force that this charge experiences is just Q V cross B. Okay. Now, if V is this way and magnetic field is downward, let's check the direction. So V is downward and velocity is this way. V cross B is upward. So that this will positive charge will be experiencing a force in upward direction. So it means that the positive charges will go up, so that there will be positive signs here. And then where will they come from? Actually here. Actually, what's happening is that the charges are not moving to the top, but electrons are moving from top to the bottom. So electrons move bottom. Why? Because if the positive charge feels a force in upward direction, electrons will feel the force in downward direction, because their charge is negative. So electrons will accumulate on the lower part, and the upper part will be, of course, having positive part. But actually, what happens is that this is not only this part plus and this part minus. These charges are distributed everywhere. More intense here, but less intense there, right? So it's like the continuous thing. So this is minus minus, okay, but it's not really. If you look at the charge Q, okay, so it will be positive and then negative there. So the charge will be moving from positive values to negative values continuously. It's not like only one region is positive and the small region is negative or something like that. They are all distributed. Okay, so distributed, but usually the accumulation is to the edges, because we know that in the conductors, the electrons start to move to the surfaces. So it's better that they move to the surface. So in some region next to the upper and lower surface, we have plus and minus signs. So it means that we have like plus and minus electromotive force, which means that some kind of voltage is created between the two tips, between A and B. So now we know that this is happening, but now if this is not connected, by the way, if this is not connected, again, we can have exactly this potential difference, but no current is moving because this part is not connected. But if you connect this part, then there is a current moving. So in what direction will it be? So if epsilon is plus and minus like that, the current will move like this, right? So there will be some kind of current moving in this direction. It's like the loop. You know? It's like the power supply which provides this current. But if this side is open, no current is, of course, is produced. But still, there will be some potential difference in the rod. If the rod is moving, okay, in the magnetic field, it's called motional EMF. This is the thing that I had already described. So now, if this is a circuit, so what kind of circuit is this? So here we have epsilon plus and minus, right? Because of this, and the current will flow, and then of course this wire have resistance R, because if it is only wire or just a metal rod or metal system, but still it will have the resistance Y. Remember that we learned the resistance was any kind of conductors, the resistors, okay, the resistor was given by rho times L over A. So the length of this is important, and the cross-section area is important. Doesn't matter what kind of values they have, but if this is a conductors, if this is a conductor, of course this is the conductor. We're not saying that this is like plastic or something like that. It's conductor. In this case, the whole wire will look like a resistance, like say small r, okay, just r, and then the current can be given as epsilon over r, which is epsilon was given by BLV over r. Okay, so this is the current. Okay, but this is the current in the system. Also, there is another aspect, as I told you. How can we just analyze this force? Now, so the magnetic force is going to be to the left. Why? Because F equals Q V cross B, and the force that is to the, so this rod will experience a force, okay, in opposite direction to the motion, as I told you earlier. So this force can be written as minus I times B times L. Okay. Why? Because we have this expression BLV, which is epsilon, and F is remember that F is equal to Q E, but E is Q times this epsilon times epsilon divided by L, right? Electric volt per meter. So this L, so F is equal to the force is due to the electric field, and it is given by this expression. And then finally, you can end up with this kind of force on the rod. This is the force rod experiences. Okay. So although we are, because the rod is moving to the right, but the force, there is a force to the left. Okay, there is a magnetic force to the left. So this magnetic force. Remember that also the expression F equals I L cross B. Okay, remember that we had seen this. So any kind of conductor will experience a force if the current passes through the conductor. This is exactly what's happening here. The current is passing through this way from this conductor. So if the conductor is having this kind of current, of course, the current will continue to flow, right? So the current will pass through this conductor. So the magnetic field, the magnetic force is created. So now let's look what happens, okay? So here is our coil. So the current is moving this way, and this is the current, which created, and plus and minus epsilon, of course. This current direction is this, and magnetic field direction is that, and V is this way, okay? So now, if the current is this way, okay, if the current is this way, and the magnetic field downward, I cross B or L is this way, right? DL, small distance is that way. So in this case, DL cross, actually this can be written as DF is equal to I DL cross B also, right? If you consider only one little segment. So now this little segment in the wire will experience a force because of this cross product. Now, dl is this way and magnetic field that way. So if you just multiply dl by the magnetic field, which is downward, you see that the force is this way. So the force that this rod experiences is going to be in opposite direction to the force. So it's a retarding force, in other words. This force must be negative. Of course it is negative, okay? Because we have this minus ILB, okay? Because L cross B is this way, so that if you consider this is X direction, it will be minus. So this is Fx, okay? So this is the force in X direction, which happens to be in negative X direction. This is the reason that we have this minus sign there. How did we end up with this? Because L and B were perpendicular. So when they are perpendicular, there is no angle business, because remember that the cross product requires sine theta, or the sine of the angle between the two. In this case, it's just, it happens to be 90 degrees, sine 90 is 1. So this is the reason that we have this expression. This is the result of this previous case that we dealt with. So f of x in x direction, the force is given by this. So if we can write the magnetic field, okay, this is minus I B L, but the current can be written as this, right? This expression. So now minus I, which is B L V divided by R, and let's assume that this is length L, by the way, right? Length L, because we are assuming the rod length is L, so that now this is the current that we have written, and then we have another BL there. Okay, so now what happens is that f of x, which is m dax or dvx over dt, or just the acceleration in the x direction, is given by minus b square L square v divided by resistance, but resistance of this rod. Of course, the rod resistance will be very small, but still it will have a resistance value. So now what we have is that this is also Vx, because V is in the direction of Vx, so we can write it as X. So this is just one-dimensional problem, dVx. We would like to solve this equation if possible. It is possible because what we do is that we put all the velocity parts on one side and all the rest of the quantities on the other side, so that this can be written as dVx over Vx, which is equal to, okay, B squared L squared over MR, okay. Of course, you should never forget the minus sign, because we will show you that this is very important, times dt, right? So time stuff and the velocity stuff on opposite sides. So this gives you ln Vx, and then the right hand side is just minus, suppose that this is some kind of constant alpha minus alpha t. So if you solve this, you see that the velocity of this rod will be exponentially decaying function. So the velocity will decay. Okay. So here we have ln Vx, but say that this is Vx0 to any Vx, of course you need a prime there, is equal to minus alpha t, so that from this ln Vx over Vx0, the difference in the logs is the log of the ratio, as you will remember, minus alpha t. From this, if you take e to the of both sides, you get Vx over Vx0, which is equal to e to the minus alpha t. Or from this, we can get Vx0 times e to the minus alpha t. As you see, because of this retarding force, if you just pull this and release, the velocity will reduce exponentially. Okay, the velocity will reduce in time. So, but if you just keep pulling this, of course, you are resisting this force. So the force that is applied, the force that you apply, okay, should be greater than. So if force is applied once, so if you just pull this and release, and then the velocity will just will be zero. So it means that if it will just stop, it will just stop by itself, just like the frictional case. Although there may be not friction, okay, there is also a friction. We are not even considering this, but without even the friction, we see that there is a retarding force, okay, to the left, so that it's opposing to the motion. So the velocity just drops exponentially. But if you just keep pulling this with the constant velocity, it means that you are opposing this retarding force. So F applied should be greater than F retarding. Okay, retard, let's say. This is retarding force. Fx is retarding force. So this is a different perspective. So, but of course, you know, to move this rod, you have to spend some force, right? This is external force that you have to spend. So now this is really nice application of this example. Now I would like to show you that we have Faraday's law. Actually, we have seen that we already have seen the Faraday's law. It's just the way of okay, the way that we have written. So we can say that since epsilon is equal to E dot dl, okay, it's like electric field times the length is voltage. Okay, this is the same expression that we had seen earlier. Okay, this is equal to also minus d pi b over dt. So this is Faraday's law. This is Faraday's law. Okay. So now we can use some kind of application of this Faraday's law. It means that if suppose that we have this coil, big coil, and then by passing through this current, but say that it's a function of time, we can create, by using right-hand rule, of course, we can create these kind of magnetic field lines also changing in time. So we can have this case and connect it to a signal generator, for instance. Signal generator. and we can apply a sinusoidal signal to this system so that the current changes in time. So we have this current as a function of time is like a sinusoidal with some kind of frequency. But how can we measure this frequency? Of course, this is, as you see, one period. This is one period. T, the frequency is 1 over T, right? 1 over the period. So we can look at the screen of the signal generator, find out this F, this T, which is the period, and by taking the inverse of that, we can see the frequency. Actually, in signal generators, you can adjust the signal at any frequency. The frequency is already given on the display of the signal generator, so you can get any kind of frequency you want. And when you apply this, okay, and now if you insert another coil inside, so let me put another coil inside like that, and put like windings like that, and look at the tips of this. If you look at these tips, we will see epsilon. So epsilon will be equal to minus n. Of course, we need also n there, right? We forgot. And d phi b over dt. So where this thing is coming from? As you see, now this is only magnetic field passing through this inner coil, but outer coil is creating the magnetic field, which is a function of time, so that an electromotive force is created, or the potential difference is created between the tips of this little coil inside, little solenoid. Okay, so this is given by this expression, and B is due to I, which is a function of time. Remember that this was the current, which is a function of time, okay, and changing obtained from the signal generator. So this is the inductance. So some kind of electric field or electric potential is created due to the change in the magnetic field. So this is the basics of the Faraday's law. So we also remember that. So EDL is equal to minus n d phi b over dt is just the expression that we have. Okay. So also remember that Ampere's law had. Let's look at this Ampere's law, because I want to discuss about the Maxwell's equations, which is very important. Ampere's law stated that if there is a circulation in the wire, it is equal to mu0 times I enclosed. Just like Gauss's law, just like the Gauss's law in electric fields. So if there is a circulation in the magnetic field, and okay, this is due to the enclosed current. Okay. In other words, if there is a current passing through the wire, then there is a, using right-hand rule, there is a magnetic field created. Okay, it will be rotational magnetic field. So in this case, this is called, remember Ampere's law. Now we know that also there is displacement current business. Displacement current. So now if we have some kind of the displacement current should be also included here, which is really not important how it is derived, but it is very important that you put the displacement current, and displacement current is the fast rate of, due to the fast rate of the electric field. So displacement current is equal to epsilon or over area times dE over dt. Okay, so this is right here. So if the electric field is changing in time, it produces a magnetic field, in other words. So this is the right side of this Ampere's law. So now what we have seen, that if there is a magnetic field changing in time, it creates an electric field. But if there is an electric field changing in time, it creates a magnetic field. It's like the it's the symmetry in the Maxwell's equations. Okay. So now, what are the Maxwell's equations? Totally are these. Okay. So So this is the number one, this is number two, and the other one is divergence of B is equal to 0, okay, is the last one, third one, and the last one is divergence of E, which is Gauss's law, rho over rho Q over epsilon 0, okay? We had seen this and we had solved some examples in the first few chapters in this course. So these are the four Maxwell's equations that we have, and these are the equations which govern the electromagnetic theory, okay? But if there are no charges and if it is in empty space, so this term is also 0. So divergence B and divergence E is 0 for space, or just for electromagnetic wave for propagation. In air, for instance, it means that enclosed current and Q enclosed is 0 because it's just a wave moving in electromagnetic wave moving in air. Then when we assume that these are 0, then we have full symmetry. So we have B dot dl, okay, which is equal to just this mu 0 epsilon 0 dE over dt, okay, as a vector sign. And then we have E dot dl, which is equal to some kind of constant, okay, with a minus sign probably, minus sign, times dB over dt, okay, because this d phi b over dt includes dB over dt also. So, and also we have these two equations which are given by just divergence of B is equal to 0 and divergence of E, which is also equal to 0. Okay, so now what happens is that this also can be written as integral form, okay, B dot dA is equal to 0 and integral B dot E dot dA is also equal to 0 if this is a closed surface. Okay, so now this is the this is for the electromagnetic wave propagated in air. So in this case, these are the Maxwell's equations to be used, and if you can solve these equations, you can really see that the propagation properties of the waves. For instance, laser waves, and also some photonic waves, and also the waves that are coming from the sun is governed by these kind of expressions. Okay, so this is very important. Okay, so this is the end of this chapter. I would like to solve one last example in this chapter, so that we will be wrapping things up after this thing. So now I would like to solve this kind of Faraday's law, because this is a really nice application. Okay, so what we have is that we have a big solenoid like this. Remember, I told you that you can connect this to a signal generator and create a magnetic field, but inside there is a small solenoid, and here current that passes through the outer solenoid is I, and now if you look at the tips of this, okay, you will see that some kind of current is passing through. Okay, of course, you can only do this by connecting this and measuring the potential difference epsilon. Okay, so now if this current is changing in time due to the big solenoid, then the magnetic flux passing through small coil is just nothing but N times BA. But now if you look at this A, okay, so if you say that this is R, it's N times B times area, which is pi R squared. Pi R squared. Okay. But now what about the magnetic field in the solenoid? Remember that last time we see that the magnetic field just passing through the center of this solenoid is given by mu0 times n times current. That's it, right? So the magnetic field is due to the only current that is passing through this solenoid. Actually, it is function of time, so that the magnetic field is also function of time. So now I'm writing this as n times b, which is mu0 times n I, and then pi r squared. So this is phi b, right? Don't forget, this is the time changing part only. So now if you take d phi b over dt, it's just n mu0 n, but this n is the number of windings here. Say this is n equals 150. This n is 150. But this small n is due to the big solenoid, right? Small n is due to the big solenoid. And n is equal to number of windings of solenoid divided by the length. This is the number density, okay? So this n and that n is different. So if you say that this is n, this is also another n that we have here, but we are using small n in order not to confuse things. So pi r squared there, and we will have di over dt. Di over dt. So now, of course, this must be, the minus sign of this is related to, the minus sign of that is related to the epsilon, right? Remember that? Epsilon was equal to minus d phi b over dt. Okay? This is what I'm writing. So the epsilon, which is electromotive force, is minus d phi b over dt, is nothing but equal to minus n mu0 n, but this is n solenoid divided by L, okay, times pi r squared di over dt. Now, believe me, this is called inductance. This inductance. Inductance of the system together. So this inductance includes the number of windings in the outer solenoid, number of windings in the inner small solenoid, and then the radius, okay, the cross-section area of this thing, and also the length of this solenoid, which happens to be L here. Okay, so now it's equal to minus L di over dt. So this is the basics of coils. Okay, this is the basics of coils. Remember that if you have a capacitance, okay, let's do it here. So we will use this property in circuit analysis. Suppose that we have some kind of power supply, voltage given, DC or AC, doesn't matter. So we give this to the system, and capacitor, inductance, and resistance. This is what we will see. This is R, this is L, and this is C. So the voltage here is VC is equal to Q over C. Remember that? We know that Q equals CV or VC, but here VL is minus di over dt. So of course there is a current created, and if the current is time dependent, then there is a potential difference created between the tips of this coil. It's something like that. And of course VR here, okay, around the resistance is just VR, which is I times R. Very simple. This is Ohm's law. Now in the circuit elements, we have everything. So we have the capacitance voltage, we have the inductor voltage, we have the resistor voltage. And this is RLC circuit. If we have enough time, we will analyze this kind of circuit by applying sinusoidal wave and see what happens. There is a resonance and things like that, right? So, but in order to understand that, we have to really understand that if the current is not changing in time, the inductor is like the short circuit. VL is 0, it means that the potential difference between the points A and B is 0, so that this is like the wire, you know. Okay, guys, this is the end of today's lecture. So I hope to see you next week to wrap this semester up. Okay. Thank you for listening.